In problem 2.8, we are given a particle of some mass m, and it's stuck in this infinite square well with width a, and it has this initial state, psi of x comma 0, where from 0 to a half, it is the normalization constant big A, and from a half to a, it is equal to 0. And we are asked to find the probability that measuring the energy for this system at some later time t will yield the value pi squared h bar squared over 2ma squared. So the first thing that I sort of want to emphasize is that this value for the energy is just the first energy for the separable solutions of the infinite square well, because we already know that for an infinite square well, we have E sub n equals n squared times pi squared times h bar squared over 2ma squared. And if n equals 1, then we just have what we're asked here. So what we're really asking is, what is the probability to find our system in the first energy state of the infinite square well? So to do that, we're going to go back and use the thing that we defined earlier in chapter 2.2, which is that the magnitude of Cn squared is equal to the probability of being in the state with the energy E sub n. So what we're really trying to find is these coefficients C sub n. And to do that, we have to use completeness theorem along with Fourier's trick, which we've done many times earlier in problem 2.7 and earlier on as well. So let's just do that. So we start by defining the completeness theorem, which is that any arbitrary wave function, including psi of x comma t, which we're sort of trying to find in problem 2.8, can be expressed as a infinite linear combination of the stationary states of the infinite square well. So indexing with n from 1 to infinity of the summation of c sub n times little psi sub n times little phi sub n, where little phi sub n is our time-dependent function, little psi sub n is our x-dependent function, and c sub n are the coefficients at the front which dictate the probability of being in each corresponding end state. So we start by recognizing that we have defined psi of x comma t at t equals 0. So psi of x comma 0 is going to be sort of the exact same thing that we have here, except now at t equals 0, the phi sub n terms go to 1 because they are complex exponentials of e to the negative I alpha t, so e to the 0th power is just 1. So we have this, and this is apparently equal to what we've defined so far, which is this piecewise function that we have for psi. And our goal now is to find the actual values of c sub n. And to do this, we use Fourier's trick in sort of the exact same way that we've done so far, which is we start by defining psi sub m. Let's do this in red. So little psi sub m star. And we multiply that on both sides. So this is going to be equal to little psi sub m star multiplied by psi of x comma 0. This equals the thing on the left, the thing on the right, which is this summation, multiplied by that same little psi sub m star. And then we take the integral of both sides. So if we take the integral from both sides, the fact that this is orthonormal, the set of solutions for little psi sub n is orthonormal. So because of that, this is a Dirac delta function where it equals 0 if n doesn't equal m, and equals 1 if n equals m, which gives us, as a result, Cn is equal to the integral of psi sub n star times big psi of x comma 0. And since this is a piecewise function, we actually split this into two integrals. However, note that this piecewise function is equal to 0 on the right side from a half to a, so we actually only have, in reality, one integral. So we have Cn is equal to the integral from 0 to a half of a times the square root of 2 over a times sine of n pi x over a dx, where this function is just the time-independent separable solution psi n. So from this point, we actually have to solve this. So to start, we have to normalize and find what the actual normalization constant is. So we do that by setting the magnitude squared of this term equal to 1 when we integrate it from 0 to infinity, or in this case from 0 to a half. So magnitude of a squared times the integral from 0 to a half of just 1 times dx must equal 1. So that means magnitude of a squared times, and this integrates to just x, and x becomes a half, so magnitude a squared times a half equals 1, which implies that a is equal to the square root of 2 over a. So if a equals the square root of 2 over a, then these two combine, and we get a term that is equal to 2 over a times the integral from 0 to a half multiplied by sine of n pi x over a times dx. And this is just a trivial sine integral. I'm not going to bother solving it, but this ends up equaling 2 over n times pi of 1 minus cosine n pi over 2. So this is what Cn is. And remember, our goal is to find the probability of this state upon observation being in the separable state that has an energy E sub 1. So to do that, we have to find magnitude C1 squared. So to find magnitude C1 squared, we have to start by finding magnitude C1. So C1 is, or not magnitude C1, we just have to start by finding C1. So C1 is 2 over pi. Oops. Because n times pi is still pi, or 1 times pi is still pi, multiplied by 1 minus, and then cosine of pi half. And that is just 0. So this is equal to just 2 over pi. So the probability of being in the first energy state, E sub 1, therefore is equal to this squared, so 4 over pi squared. And this gives us a final result of roughly 40.5%. And that is our answer.